Our first speaker today is the Director General of ITER, the International Thermonuclear Experimental Reactor. And that's a very cool name for the most complex machine ever built by humans. Please give our first Starmus Earth welcome to Pietro Barabaschi. Good luck, sir. Thank you.
British scientist. His name was Walter Marshall. He was the chairman of the United Kingdom Atomic Energy Authority in the 80s. He once said, he was a fusion critic, and he once said that fusion is a wonderful idea with infinite possibilities, but with zero chance of success. Of course, I don't have the same mind. I wouldn't be here. I think that ITER is a wonderful project. It has limited possibilities, but it has a pretty good chance of success. Regarding fusion and its impact on society, that is a little bit a more complex question for which I don't yet have an answer. But I strongly believe that we should get first ITER proof that there is a chance, and then I believe that with some other ingredients, at some point humankind will be able to master this technology and this wonderful potential energy source. So thank you for inviting me here. It's a great honor to be in front of you. I will speak briefly about the ITER project. The ITER project is a project that was born in the late 80s as a project of peace. It was an idea of President Gorbachev and Reagan, who wanted to cooperate after the Cold War on something very complicated. And as it was just said, it is indeed very complicated. I can testify for that. And the two members, Russia and the United States, then were joined by the European Union and by Japan. This was in the 90s when the ITER project started to be designed. I had personally the privilege to be part of the team in those days. And then in the early 2000s, three more countries joined. This is China, India, and South Korea. So we have in ITER more than 50% of the world population. We have, say, more than 80% of the world industrial potential. You don't get to see nowadays, this is a question I get asked very frequently now, you don't get to see nowadays these 7 flags next to each other in many other places, but if you come to ITER, you will see them and you will be able to witness that we are all working together for this project without, say, having any impact of the global situation. I think it's really a project of Homo sapiens. So I borrowed this image from your website, the Starmus website. We speak about fusion as the process that powers the stars. So indeed, it powers the sun. What we can do on Earth is not exactly what happens in the sun. The sun is fueled mainly by protons fusion, the fusion of 2 protons. In the case of this type of fusion reaction, it is necessary to have extremely high densities. So in the core of the sun, the density is about 150 times higher than the one of water. That would mean that a liter of soup of the plasma that it's in the center of the sun would weight on Earth about 150 kilograms. Naturally, we can't do that. We don't know how to do that because we don't have the means, at least not for any significant amount of time, to concentrate matter so much. So we have to use something different. And what we do is that we use a different fuel mix. We use two isotopes, two nuclei who are much more affine to merge. They are deuterium and tritium. They are, say, different species of hydrogen. Deuterium is rare, but it's frequent, say, it happens. It's naturally present in the atmosphere. Tritium is more exotic. It is constituted by a proton and two neutrons in its nucleus. So it is still chemically acting like hydrogen, but it is heavier, and it likes to merge with deuterium to start a fusion reaction that gives rise to significant amount of energy. So I said that it's easier, of course, than proton-proton reaction, significantly so. So much so that I could say that proton-proton reactions, which are essentially not feasible on Earth, would not even be practical, because the power density that they generate is too little. I will come to that later. So the technology of fusion requires the achievement of extremely high temperature, 150 million degrees, which is still higher than the one in the core of the sun. And we now know, after so many decades, that we have to create a fireball which have a linear dimensions of about 10 meters or so, a little bit more than that. Smaller doesn't yield to the sufficiently high temperature because the confinement time is not good enough. So it's a bit like a bonfire or a pizza oven. It has to be big enough in order to reach the temperatures that we would like. The trouble with that is that as we make a bonfire bigger, the power density on the surface becomes higher, because while the generation of power in total goes with the third power of linear dimensions, the surface goes with the second power. So the bigger is the bonfire, the stronger is the power density at the edge. And that creates a very significant technological difficulty with nuclear fusion, as we need to have such big devices. So we have to find the right compromise, and we have to develop the right technologies to withstand power densities that you can find in, say, the nozzle of a rocket. And it has to work all the time like that. So maybe this is one of the reasons why Marshall was a little bit skeptical. But we are working on this technology. And just to speak about power densities, the power density in the core of ITER will be about 1 megawatt per cubic meter, and on its surface about 1 megawatt per square meter. If you look at the sun, it's remarkable. Not everybody knows that the power density in the sun's core is a few hundred watts per cubic meter, which is less than the power generated in our body. So it becomes very hot because it's so big, and it's really big. You can trust me on that. So what is the mission of ITER, defined in the late 80s? It is very, very broad. It's to demonstrate scientific and technological feasibility of fusion. It doesn't speak about economy, and I think it's an important point that I shall touch later. It should reach burning plasma, and it shall do so for a significant amount of time. See, time is important, you see, because we really have to get things in such a way that thermal equilibrium is reached. It has to demonstrate that it can self-generate the fuel that it requires, because tritium cannot be found anywhere. We can produce it in some exotic ways, but the idea is that fusion reaction should fuel itself, at least for what concerns fusion, tritium, which will be bred by having neutrons interacting with with lithium. It has to have a power enhancement factor on the plasma of greater than 10. And very important, it should also demonstrate some of the safety characteristics of fusion potentially for a power plant. So I spoke about size, and I want to give you some references. The JET project that was built, thanks also to the interest of UKEA, the JET joint undertaking. Similar projects were built also in Japan and in the United States, the FDR and JT60. Yes, this was built in the 80s, and you can see its size. It had copper magnets. We finished last year, we completed JT60 SA, which is the evolution of JT60 in Japan. It's a superconducting machine, and it will reach, say, conditions which are not those that are, say, will be reached in ITER, but it will support the ITER project in its research. And then you can see ITER. These are the magnets. I'll speak about magnets. Why do we need magnets? We have to get this fireball, but how do we keep it? How do we contain it? We don't have gravitational forces that can do that. It would just like to disperse like hot gas. And so we use magnetic fields. We have, with magnetic fields, to confine it. And I mean, for me, not necessary to go in details on how this works. But fundamentally, that is the principle. So we need a very, very large and powerful magnets. And in fact, what you see here are two of the magnets that build the torus of ITER. And now you see here what you would see now in the assembly hall of the ITER project in Cadarache. I repeat my invitation to come and visit, because you will feel a little bit better than what you can feel here in 2-dimension, the magnitude of this magnet. And this is a view from below. And that's part of the innovation that was necessary for ITER. We had to develop novel technologies on really massive scale. Nobody ever built anything like this. And the precisions at which we have to fabricate such big magnets is remarkable. These magnets, they have to be machined to 1/10 of a millimeter, and they weigh hundreds of tons with linear dimensions, as I said before, in the region of 10 meters or so. So there are a number of challenges that we require in so many fields, in nuclear fusion, in materials, in power conversion, heating systems, and cryogenics. We need a very, very big refrigerator in ITER, and et cetera, et cetera. The challenge is not only in innovation. I spoke about ITER as a project for mankind, a project by Homo sapiens, and Homo sapiens have different cultures. And when we work together, it's surely a challenge, as you can imagine, to have so many cultures working together on a common project. The project is common, so the idea and the achievement is the same. But nevertheless, naturally, the work done by the members, the governments, as well as within the project, presents some of its challenges. But I think it's part of our DNA, and I think we are proud of that, that we can, notwithstanding everything, we can continue and work along this project united. So I have now a 30-second movie that will give you a view of the site. Dimensions here are in the neighborhood of a kilometer. And what you see central is the assembly hall and the tokamak building. But I will now be silent for 30 seconds so you can see this very brief movie. Yeah, what we end up here, it's the pit. It's where it's a cylinder, a cryostat, where all the machine will be installed. It is in the process of being assembled, by the way. And a couple of years ago, one of the sectors was installed, but we had to pull it out because we had to fix a problem in a thermal shield. We found a very small issue, but we decided that it was necessary to fix it. So let me say the project had its own problems along the way. It was not certainly smooth sailing. It had a difficult start. In 2016, there was a new baseline, a new management. It was put, I think, in a pretty good shape. Then there was COVID, and the impact of COVID, I think, was directly and indirectly very important. And we had some technical problems. So we are now in the process of defining a new timeline. In fact, we will present the new timeline to the governments of the members in 3 weeks. So we are really hectically preparing this and defining a new one and defining a new cost estimations. So I am not in a position to say today when we will proceed with the thermonuclear reactions because the governments, the stakeholder, they ask us first to present this to them. So now you have heard, and you have surely some questions about what is going on in the world, because there are a lot of startups, there are a lot of initiatives, particularly in the private sector, which are popping up all around the world, in particular in the United States and in Europe and in the UK. And I think it's normal to ask what's going on, how is ITER going to relate to these startups? And I think it's, from my perspective, it's very good news that so many people are investing and so many people are developing new ideas. And what we would like to do in ITER is to provide some knowledge, some experience to some of these startups. So what is going on? You see, in science, I think I'm saying a platitude here, but normally when we go to conferences, we present successes. When we send a paper to a journal, we present good stories. And if we would send to a journal a story about, let's say, a dead end or something that doesn't work, it wouldn't necessarily be published. I would say it would not be published, period. So what, on the other hand, we have developed with ITER is a lot of knowledge about what works, but also of things that didn't really work out as we hoped. And we would like to share all this knowledge that was developed essentially with public money with the private sector. So we will start some workshops in ITER where we will try to have an approach for knowledge transfer to startups, naturally from the members, to make sure that our project can be of value to all these new ideas right now. So now question could be, what are the remaining challenges? ITER will address some problems, but not all of them. So then I come to say a summary about fusion in general. So there are 4 fundamental questions in fusion, at least to my thinking. The first one is, can we get fusion on Earth? And the answer is yes, we have demonstrated this. We know, and we know this from quite some time. The second question is, can we get out of this reaction more energy out than the energy we put in? And also this question has an answer. We have proven that the answer to this question is yes, we can. We can do so for a brief amount of time. And you may have heard, you may have seen just, say, 1 year or more ago about an experiment in Livermore where, with a different approach, this was achieved, and we have an answer to this question. The third question is, can we get more power out than the power we put in for a long period? A long period is what? A long period is, you can imagine, with your car, you want it to reach thermal equilibrium until you know that the engine runs smoothly. And it takes about a quarter of an hour, half an hour. So this is an answer that we will get from ITER. ITER will produce 500 megawatts of thermonuclear power with a plasma gain, energy, power gain of 10 or more for, say, a long fraction of an hour. Depends on the condition, could be, say, a quarter to an hour to half an hour. The fourth question, it's more complicated. The fourth question is, in fusion, can we get more money out of the money we put in? So that is a question that will allow us to say whether fusion can be practical for society, whether, yes, Mr. Walter Marshall was wrong. So to respond to this question, ITER, I'm afraid, will not be enough. There are a number of big questions that need to be answered, and for which now activities are ongoing in the world and have been ongoing. Materials and the ability to have high-power heat exhaust, and also the maintainability that will determine the availability of the project, the ability to manage the tritium fuel cycle, and then efficient heat removal. So all these things will have to be addressed in parallel to ITER, and I expect also after ITER. So I wish to thank you again for your attention. I hope I could give at least an answer to some of the questions you had on fusion. And once again, all of you, you're invited to come in the south of France, in Cadarache. It's a beautiful area, by the way. Okay, you can see some snow sometimes, but mostly it's sunny there. Thank you.